Okay, example 3 wants us to find the double integral over the surface, so it's a surface integral, of x squared ds. If S is the unit sphere, x squared plus y squared plus z squared equals 1. So it wants us to find the surface integral over the entire unit sphere. The x squared in the integral basically serves almost kind of like the density function in this case. So what we're trying to do is we're trying to find almost the, like I said, it's the surface integral, almost like the density or the mass per unit or whatever. That's the general idea here. So that's why it's variable. It's a variable density or variable change over the surface. So we're going to go ahead, and this is over a sphere, so it seems pretty obvious we should go in spherical coordinates. So x in spherical is rho sine phi cosine theta, but remember in this case rho is 1 because it's just over the surface. So 1 sine phi, I'm just not going to write the 1, so it's sine phi cosine theta. Here we'll say it out here that rho is 1, so we know that. Y is going to be sine phi, or 1 sine phi sine theta, and then z is 1 cosine phi. So there's my parameterization. So r now is going to be in terms of phi and theta. So again, we took x, y, and z, reduced it down to 2 variables. So we get sine phi cosine theta, sine phi, phi, let's erase that, sine phi sine theta, and then cosine phi. And if you remember, because what we have to do is we have to find r sub phi, r sub theta, cross those. If you remember from 16.6, we don't need to do that whole process, because anytime we parameterize a sphere, the magnitude of r phi cross r theta is a sine phi, or where a represents the rho part. So I'm sorry, not a, it's a squared. So it's rho squared sine phi. But in this case, of course, rho was 1, so 1 squared is 1, so we just get sine phi. So I didn't have to write the whole thing down, but again, it's because we're parameterizing a sphere here. So we're always going to get that rho squared sine phi for the cross product. So now we can go ahead and set up the integral. Well, let's see. It's a sphere, so we know that theta goes from 0 to 2 pi. So theta goes from 0 to 2 pi. Phi goes from 0 to pi because we want the whole sphere. And then we have x squared. Well, x was sine phi cosine theta, so we're going to square that. So we get sine squared phi cosine squared theta. And then times our cross product, which is sine theta d phi d theta. And I apologize, that should not be a sine theta, that should be a sine phi. That was our cross. Alright, let's see, I think we can split this up and do 2 separate integrals. Neither of which will be horrible. We do have to do a little bit of reduction on these things, and it looks like a u substitution, but shouldn't be horrible to do them. So let's go ahead and split this up. So let's see, theta was 0 to 2 pi, and that's going to be cosine squared theta d theta. Phi is going to have a sine cubed. I'm going to leave it, however, as sine squared phi sine phi d phi. In case you did not remember this technique, this is what you're going to have to do in order to reduce sine cubed. Alright, so let's go ahead and take a look. Cosine squared, you need to use the reduction formula for that one, which is, let's see, cosine squared is 1/2 of 1, it's plus cosine of twice the angle. in order to do the phi part, we're going to have to change sine squared phi into 1 minus cosine squared phi. Keep writing theta. There we go. Sine phi d phi. So the first one will actually be pretty easy to do. I can pull the 1/2 out to the front, and then I can take the antiderivative of 1 plus cosine 2 theta. So the antiderivative of 1 is just theta. Antiderivative of cosine of 2 theta, remember, is 1/2 sine of 2 theta. And we'll evaluate that from 0 to 2 pi. Over here on the right one, we're going to have to do, like I said, a u substitution. So u here is going to equal cosine phi. So du is going to equal negative sine phi d phi, or d phi is going to equal du over negative sine phi. And I'm going to go ahead and change the bounds. So if I plug 0 in, cosine of 0 is 1. If I plug pi in, cosine of pi is negative 1. We're going to have 1 minus u squared times sine of phi times du over negative sine of phi. I'm glad I have that negative there because it's going to flip my bounds for me. So the sine phi's are going to go away. The negative is going to flip my bounds. So we're going to end up with an integral from negative 1 to 1 of 1 minus u squared du. That should not prove to be too difficult. So the antiderivative there is going to be u minus 1/3 u cubed from negative 1 to 1. Okay, let's go ahead and bring the other piece down. We can kind of finish that one off as we go. So plugging in 2 pi on the left-hand piece here, let's see, we're going to have 1/2. So if we plug in 2 pi, we're going to get 2 pi plus 1/2 of sine of 4 pi, but sine of 4 pi is 0. And if I plug 0 in for theta, that's 0 all the way around. So really what I just get over there is 1/2 of 2 pi, or pi. So we'll bring the pi down and keep multiplying that one. And then if I plug in the 1, we're going to get 1 minus 1/3. If I plug in negative 1, we get negative 1. That'll become minus minus, so plus 1/3. So 1 minus 1/3 is 2/3. Minus a minus 2/3. Don't forget to bring down the pi. So we're going to get 4/3 pi, or 4 pi over 3. That is the surface integral of that sphere. All right, fourth example, probably the easiest one that we do. We want to find the surface integral of x minus y minus z. So again, that's kind of like your density function or whatever on the surface. It's part of the plane x plus y equals 1, and z is going to range from 0 to 1. So if we sketch this, see why this one actually becomes pretty simple. It says that the plane is x plus y plus 1, meaning that if x is 0, y is 1. So we'll put that there. If y is 0, x is 1. And it says z goes from 0 to 1. So really, this thing is just basically like this, and then it goes up a vertical distance of 1 unit, something like that. So this is almost kind of like the window or whatever that we're looking at there. That's the surface that we're trying to take this on. So again, this is a plane. It looks like it's going to be pretty simple to use a trivial parameterization here. We can let, in this case, we can let x equal x. Y can't equal just y, because technically if you solve this thing right here for y, you're going to get y is a function 1 minus x. So y is the one that actually is going to have the other variable in it. And z in this case is just z. So we still have x, y, and z as a function of just two variables now. In this case, they just happen to be x and z. So we know that x, well, according to this, x goes from 0 to 1. So 0 is less than x is less than or equal to 1. And z, it already tells us, goes from 0 to 1. So that's really nice right there. So we've parameterized it. We know that when we reduce this thing from the ds into the dA, we're going to need to do this in terms of the cross product. So let's see, we're going to need r sub x. So I guess I should probably write r. I'll write r over here. So r of x and z is going to just be x 1 minus y z. So r sub x is going to be 1, 0. No, I take that back. I wrote my parameterization wrong. That should not be 1 minus y. It should be 1 minus x. Makes a big difference. 1 minus x. So that means that what we have here is 1, negative 1, 0. And then r sub z, or the partial with respect to z, is 0, 0, 1. Yeah, that looks right. Okay, so we need the cross of those two. Eliminating I row and column gives me a negative 1. Eliminating the j row and column gives me 1 minus 0, which is 1, but we change the sign. And then eliminating the j row and column just gives us 0. This is really nice because these are all constants. So the magnitude of rx cross rz is the square root of 1 plus 1 plus 0, which is just square root of 2. So that's actually really nice. So now we're going to go ahead and write our double integral over our new domain, but again, it's the domain of the parameterized. It's not the domain as in the projection. It's the domain of the parameterized. So it's going to be, let's see, x goes from 0 to 1, and so does z, so that makes that easy. Of our original function, which is x minus y minus z. But remember, it can only be in the two variables. It's got to be in just terms of x's and z's. So x is fine. Got to change y into what it was, which is 1 minus x, and then minus z. Can't forget to multiply it by the cross, which is square root of 2. And then dA, which is going to be in terms of x and z. In this case, it doesn't look like it's going to make any difference which one we do first. So we'll just do dz dx. Doesn't matter. You could do dx dz. Doesn't make any difference. All right, so let's go ahead and work this double integral out. This should not take very long. So let's see. We've got integral from 0 to 1, integral from 0 to 1. X minus minus x is 2x minus 1 minus z. I'm going to pull that square root of 2 since it's a constant out to the front. This one we cannot separate because the x's and z's are not being strictly multiplied. They're being added or subtracted, so we will have to go through the process. Take the antiderivative first with respect to z. And we're going to get 2xz minus z minus 1/2 z squared from 0 to 1 dx. So still got a square root of 2 on the outside. So let's see, plugging in a 1 for our z's, it's going to be 2x minus 1 minus 1/2. Plugging in 0 for the z's makes them all go away. So really that's just the square root of 2, integral from 0 to 1 of 2x minus 3/2 dx. And then we'll take the antiderivative with respect to x. So we're going to get, what is that, x squared minus 3/2 x from 0 to 1. So we get a square root of 2 on the outside. Plugging in a 1, we get 1 minus 3/2. Plugging in 0 makes that whole thing go away. So it looks like I'm going to get 1 minus 3/2, which is negative 1/2, or negative square root of 2 over 2. And that's the surface integral for that particular part of that plane.